There you go. Okay, so I'm going to start talking about two concepts that are really important in robotics problems, and these are robustness and resilience. And I just want to take this illustrative example here. The robot's name is Spot 1 at the DARPA Subterranean Challenge. And so in that case, Spot 1 we would say Spot 1 was not robust enough to avoid falling down, but it had this resilience capability embedded into it, which enabled it to get back up and start working again. So more formally, when we talk about robustness in robotics, we refer to the robot's ability to maintain some efficiency of functionality in the presence of stochastic disturbances. And you can think of these disturbances as forces applied on the robot, things that delay the robot, or even just variations of your tasks that you didn't expect. When we talk about resilience, we kind of implicitly assume that the robot has already endured the negative effects of these disturbances, such as falling. And by resilience, we refer to the robot's ability to kind of recover back to normal behavior after that. And we really need, in practice, we need both robustness and resilience in a robotic system. And this is especially important if we're using it in safety critical applications. We want to be able to trust the robotic autonomy. And that's why these two concepts that we're going to talk about a little bit more are really important. So my work isn't about getting a robot back up after it fell. But instead, what we're going to do is that we're going to look at two different application areas in this talk three thesis. And in each of these application areas, we're going to try to analyze how uncertainty affects the problem. And they all kind of have their own specificities. And we're going to try to build, in our case, path planning algorithms with these idea of robustness and resilience in mind. So just to introduce a bit more, sorry, we don't see the title here. In the title of the thesis, there is environment representation and path planning. And just to explain what these are. So when we want to launch a robot into the wild, as at Stanford University, we're going to, when designing the robot, we're going to pick sensors that are going to enable it to perceive the world. We're also going to design, to pick actuators that are going to help it move in the world. And everything that kind of comes in between the robot's perception of the world and its mobility functions constitute what's called the robotic autonomy stack. And you can break this into state estimation and mapping and decision-making and planning. By environment representation, we refer to we refer to a structure that represents as much of the world as possible and all of the task relevant information as possible. So it's a representation of the world that the robot builds. And the path planning algorithm comes into the decision-making part of this work that takes in this environment representation and returns, in our case, paths that satisfy a mission objective. The point I want to make here is that you really need to design the environment representation and decision-making algorithm jointly, because the problems that are going to affect one are also going to affect the other. So if you have errors or disturbances affecting your environment representation, it's going to propagate into decision-making. And the decision-making algorithm, it's going to be subject to some computational limits. We can't, unfortunately, solve all the problems that we would like to perfection. And we need to design the environment representation while thinking of this as well, try to get the best structure we can for solving our problem. So the question we're asking in the thesis is, how do we create robust and resilient path planning algorithms with, in our case, with sparse environment representations that are able to scale well to large environments? So I'm going to give a small overview of each of these areas of application before diving into two of them actually that I'm going to present today. The first that I'll present is unknown environment exploration, and the second is human-robot interaction. So for exploring unknown environments, this project was actually a collaboration with the team at JPL, and that was around 2020, 2021, and they had a team that was participating in the DARPA Subterranean Challenge. This challenge is made to kind of imitate some disaster response scenario. The purpose is that we want to send autonomous robots into these subterranean environments that pose navigation and perceptual challenges for the robot, and try to have the team of robots cover or explore as much of the environment as possible. And in that case, it was in order to locate artifacts. On the lower left here, the robot's exploring a cave at the Lava Beds National Monument, and you could see the environment representation being built as it explores. Now, this problem is especially challenging in particular because we don't assume any prior domain knowledge on the environment to explore. So the robot builds this representation as it sees it in real time. And so a problem to solve here is, how do we plan for hour-long missions on a graph that constantly changes as the robot explores? Okay. There's an extension of this project. This is chapter 3 in the thesis. I'm not going to talk about it today, but it's also this idea of exploring unknown environments, but this time we're searching more specifically for the source of a radio signal. And this problem is challenging because the robot has to look into how it should explore the unknown space, although it doesn't know anything about it. The third area of application is human-robot interaction. Now, it might be a little bit less obvious to see how this relates to robustness or resiliency. When you send a robot into like a real-world environment, there are people around, and even though your robotic system can be really good at solving these optimal decision-making problems on its own, what happens sometimes is you throw humans into the loop, and your system kind of falls apart. So a robot that is able to listen to what the people around are trying to tell it is also, in this sense, a resilient robot. The question we're going to ask here is, how do we model and infer a human's path preference from indications in robotic navigation? And the final area, which I'm not going to talk about, is centralized multi-agent pathfinding. Sorry, I should remove this. We're looking a bit more at these controlled factory settings that are, if you've heard of the terms like flexible manufacturing, factory 4.0, the idea is to build coordination algorithms for multiple robots that are robust to all the kind of things that could happen in this factory. And in that paper, we focus on delays in travel time. Okay, so now I'll get into the first project, which is exploring unknown environments. So just to summarize, there's very little domain knowledge, perception, navigation difficulties, and we want to find how to explore these environments efficiently and reliably. Okay. So as I explained, our problem here is to design a planning solution for a robot to explore a maximum amount of unknown area within a limited mission time. And I'm just summarizing some of the challenges here. The mission time is usually limited by the robot's battery life, and this could be, for example, on the order of an hour. Sensing isn't perfect, the environment is denied of communication, so that's not the focus of our work here. But these environments can be particularly large, so we're looking at representations that can really scale to more than hundreds of meters or even kilometer scale. So the way that we represent unknown environments, especially these large environments, is by creating a sparse topological map of the explored space. And this is a really commonly used solution. So we create this graph that represents the topology of the explored space. And you can see as the robot explores, it notices areas that are potential good areas of exploration. So these boundaries between known and unknown space, they're called frontiers, and we encode them as nodes in the graph. So then we can define our path planning problem over these frontiers. So what we want to do is define the path, so in other words, a sequence of frontiers to explore, that maximizes the information that the robot can expect to collect during mission time. And you could use different kinds of metrics for information gain. Oftentimes we talk about coverage problems. We kind of refer to the ability of the robot to sweep as much area as it can with its sensors. So this information gain would be an estimate of how much area it thinks there is to explore beyond each frontier, for example. So I've been talking about model uncertainty, and I want to give two example problems to motivate this. So I said that in reality, we don't have any prior on what the environment's going to look like. And here are two different problems that actually share the same underlying structure. So these yellow boxes, you can see them as frontiers, and the cost to go between each frontier is the same in both problems. But in the cavern problem here, we're going to assume that each of these frontiers leads to a new pathway and a hallway to explore that can extend as far as we want. And if we know we're in the cavern problem and we're trying to find a path that helps the robot explore as much as possible, then the best solution is simply to be greedy. We would head first to the closest frontier, so that arrived at the frontier, we would just explore indefinitely. The parking lot problem is fundamentally different, because here we're going to assume that the frontiers actually just represent little areas that the robot hasn't seen quite well, and there's nothing to explore behind it, or nothing much. And in this case, the way we actually want to solve the problem, it's similar to this notion of traveling salesman problem. It's actually a variant. It's a different problem called orienteering. And the robot's going to try to find a strategic plan to explore as much of these frontiers as it can within its limited time budget. Where I want to go with this is that the future structure in the environment, it's never going to be exactly the cavern problem or the parking lot problem. It's actually really difficult to predict and even to model. And I'm insisting on that because we're going to come up with a formulation of the problem and a heuristic solution to this. I just want to highlight this, kind of open-ended component of the problem to try to motivate why we formulate it in this way. So the literature in unknown environment exploration, there's a subcategory of it called local exploration, where the robot tries to efficiently explore a known area that's right in front of it. We're interested in the other subcategory called global planning, where we try to make these strategic decisions over the full temporal and spatial extent of the problem. And because there's such high model uncertainty here, the solutions are usually divided into two kinds of approaches. The first one are one-step look-ahead policies, like the greedy solution that we saw, where we assume really high model uncertainty and just pick the most promising frontier to head towards. And there's alternative multiple step look-ahead policies, which is the one we're going to propose here. So let's first suppose that we're trying to solve a parking lot problem. Let's suppose there's no model uncertainty and our environment representation is completely accurate. Then, as I explained before, the problem we're trying to solve is called the orienteering problem. And we're trying to find a path or sequence of frontiers that maximizes the total information gain the robot can collect, subject to this mission time budget. Now, I joined the team at JPL that they had tried a lot of different approaches, depth first search and greedy search. And when I arrived, the first thing we tried was orienteering. And it actually did work well for a while until we started to notice these kinds of solutions sometimes. So on the right, I'm plotting the solution to the orienteering problem. And you can see kind of the problem with this is that the first node in the solution is located really far away from the robot. And by doing so, the orienteering problem has no incentive for the robot to visit frontiers early in time. And this is actually not right. This is actually not a behavior that we want to have for multiple reasons. So there's we're in environments with large navigation risks. We don't want the policy to oscillate as our environment representation changes. But more importantly, the orienteering problem is just not well suited to robotic exploration because we falsely assume that the graph stays static over time. So what we do to solve this problem is that we introduce a variant of the orienteering problem that also has this idea of long-term exploration, strategic long-term exploration in mind, and we call it the front-loading information gain problem. So what we do is that we provide a heuristic incentive for the robot to visit frontiers earlier in time. And to do so, we design this function that we call a front-loading function that provides some reward term for according to the path distance of the frontier on the solution. By doing so, we produce solutions where reward accumulation is shifted earlier in time. And so I'd like you to look at this figure on the left. I think this is probably the most important figure of this part of the presentation. What we're plotting here is the expected accumulated information gain according to the distance along the path. And we obtained this plot by running all of these different methods on many consecutive iterations. Now, the greedy solution is short-term efficient, which is what we see here. It accumulates information gain really early, but it doesn't do really well when we look at the long term. The orienteering problem, the orienteering method assumes no model uncertainty and is long-term efficient, but there's no incentive for collecting information gain earlier in time. And so we kind of see the strategic balance that we're trying to hit here. We want to collect information gain early, but without renouncing to the efficiency in the long term. And so when we apply this front-loading information gain method to the same problem that I showed, the first action is a lot closer to the robot. So in case you might be wondering why we chose this kind of logistic function as a heuristic incentive. And when we were designing these functions, one of the things that we had in mind was this idea of robustness to errors in perception. The problem we had with exponential discounting, which is maybe the more first approach to incentivizing collecting reward early, you can see the derivative of this function is highest for low path distances. And the consequence of that is that our solutions are going to be very sensitive to variations in path costs. So to test that, we found a data set of a robot, this is Husky 2, exploring this big pile of rubble. And this was really stress testing the perception algorithm. So the costs here were kind of jumping around. And we noticed that by discounting exponentially, we obtained a lot more differences in the consecutive heading angles of the robot as the robot explored. And we really don't want this because it causes just the robot to slow down and not be very efficient. So we compared our FIG-OP front-loading information gain approach to next best view, which is this one-step look-ahead method, orienteering, and 3D solutions. And we made these tests by running the autonomy stack in these simulated environments. The first one is the maze, and the maze looks a lot like the cabin problem, in that generally the best thing to do here is to pick the closest frontier, and it's going to lead to a passage to explore. And kind of consistently with this, we do notice that all of the methods that have some greedy component to it kind of perform similarly here, but the performance of orienteering drops. On the other hand, the structure of the subway station is very different. There's these large rooms that the robot needs to explore. And we kind of notice an interesting behavior here. So at the first part of the mission, there's a lot of model uncertainty. The robot has no idea what's going for. So the methods that have the high coverage rate are going to be those with the greedy incentive. But once the robot has explored sufficiently, the model starts to become accurate. And that's where we see kind of orienteering and FIG-OP kind of get the highest coverage rates. So overall, thanks to this kind of trade-off we do between short-term and long-term efficiency, the method we propose is able to cover the environment in the least time and maintains a good coverage rate overall, which was what we were looking for. I'm going to go a little bit maybe more quickly on the hardware tests. I think one of the things that I want to show is that this happened in the DARPA challenge. In the DARPA challenge, the area was really difficult to explore, and we stress tested the robust perception system. And you can see how brittle the representation of the environment was as it explored. So I guess the takeaway we had from this is that, I guess even more important than being long-term efficient in this case, we really wanted to find a method that would really be consistent and as stable as possible and as robust as possible to these changes in representation in order for the robot to be able to explore despite all the perceptual errors that occur. So as a takeaway, we looked at the unknown environment exploration column. We saw that it was characterized by a very high amount of model uncertainty. And we proposed this heuristic path planning solution to kind of reconcile greedy and orienteering policies. Okay, so now I'd like to move on to the second part, which is incorporating human path preferences in robotic navigation. I guess before we go fully into this, I just want to motivate what we're going to do a little bit. And it's kind of like a funny video. It's just a little break in between the two projects. But it's a good example case of why we're going to do for the next project. So we took this video. It was about 5 days before the subterranean challenge. And we were in a very big mine in Kentucky, and we were doing these big tests. We would deploy robots and try to stress test the system. And this is spot one exploring the mine, and I'm spot one safety operator that day. And you're going to notice that, there we go. Right at this point, the robot stops, even though its planner is telling it to continue moving on forward. The reason is that I stopped it, and you can see why in this little figure on the bottom left. I stopped it because it was heading into this giant puddle, and it probably would have been fine. But yeah, we were 5 days for the competition. We already had an instance where one of the robots fell into the stream, so we didn't really want to risk it. And I decided that, okay, it was time to stop the robot. And now the mission was to get the robot out of here and try to get it to explore another area. Now this proved to be really difficult. So this is kind of a chaotic video where the first thing I tried to do is I grabbed the remote and I tried to steer the robot away from there. Fortunately, there was a technical problem. The robot wasn't responding well to the remote, so it was just insisting on this path there. So the second thing that I tried was just I got the radio and I started complaining to the people at the base station. Okay, the remote control's not working, the robot's stuck, I need you to send it to this other goal there. So obviously the people at the base station are busy, they have other things to do, so the robot keeps just turning in circles. Okay, you're gonna see one of the next things I did, I think I jumped that passage, is kind of out of desperation, I just go in front of the robot and I try to be an obstacle, hoping that it's going to cancel its goal. Fortunately, that doesn't work. The robot says, yeah, I can go around you. Okay. And at some point, okay, finally the operators at the base station finally managed to give it another goal. I don't know why I took this video, but okay, and I guess, yeah, the takeaway from here, I'm not just showing this video to keep my friends awake, but the point I want to make here is that the robot was really doing well on its own, and it probably would have been fine in that area. But suddenly, I intervened and tried to indicate to the robot that I wanted to go away from there. And it ended up in like a 5-minute fight between me and the robot. And this is, I'm going to move to the next slide. So this is exactly the motivation for the second project. What we want to do is, when we send the robot in environments with humans, they are potentially going to have a lot of things to say to them. And we want the robot to be able to infer what the human's trying to say and adapt to this with our lens here of robotic navigation and path planning. And actually, there's a paper, a project from Indra Bashti, I think from Berkeley, where they kind of work exactly on this problem, but in the context of robotic manipulation. So manipulation of, for example, a cup. And they have this example where, they you can imagine a robot like unloading things from a dishwasher. And so it's carrying these, for example, a cup around. And the problem they're posing here is, okay, maybe the robot's carrying this cup way too high. And there's a human there looking at the situation, and they're thinking, okay, I want the robot to carry this slower because it's less risky. One of the things they're likely to do is grab the robot arm, for example, and just press so that it gets lowered. And if you don't account for, well, there are several ways the robot could behave in that case. You could kind of reject the force that the human is pressing and treat it as a disturbance. You can also maybe comply with it, but once the human releases their arm, the robot will just spring back to its previous risky position. And the way they approach this problem is that they try to encode and infer the intention of the human, and they do this by encoding intention through some parameters that are relevant to the problem. And inferring what these parameters are as they collect observation in order to adapt to them. So this is exactly the problem that we're going to try to solve in the case of path planning. And we're going to focus on how do we encode and infer path preference in this case. Okay, so there are some contributions in the literature that do something really similar to this. I guess one of the first approaches we considered was trying to infer the goal of the task. And then from the distribution that you have over the goal, you can kind of turn this back into a distribution over trajectories or over paths that we think the robot's going to want to take. There's also very similar work in the area of robotic manipulation, where you try to guess, for example, which object the human wants to grasp. And once you're confident enough on what this object is, you can start assisting the operator in this task. Now, let's say that we only want to infer what the goal of the task is. This is kind of how we would formulate the problem. So the slide is a little bit dense, but the state of the world is going to be composed of the robot's location and the human's intended goal. And well, because we don't know what this goal is, we're going to maintain a belief distribution over this. And we assume there's a discrete set of candidate goals. And we're going to assume some observation model for the human. And our goal is to assist with the task. And for example, this could be carry the table to the correct goal. And the optimal solution to this problem could very well be this. So in this case, thanks to the human's observations, we correctly inferred that the goal we wanted to go to was this one. But it turns out the shortest path and maybe the lowest cost path to the goal for the robot is this one. And just visually you can notice there's a problem here. The human's kind of pointing with their joystick for the robot to go on the left side of the table, but the optimal solution kind of doesn't account for that. And what we want here is really a way to infer the human's path preference, even if their preference doesn't match with the lowest cost path, with the cost being what the robot thinks the cost is. And to do so, we need to encode the human's path preference, and we call theta the variable to encode it here. Okay, so we saw that methods that you kind of assume the goal, infer what the goal of the task is, they require very little human intervention, but your error can be high if your preference kind of differs from the lowest cost. And there's another area of research where we try to infer what we think the human's preferred way to solve the task is. And these papers are kind of often relevant to the area of shared autonomy. In this case, we kind of assume that the person will be an active collaborator in the task, and we're going to share the autonomy between the operator and the robot. Now, this isn't exactly the kind of case we're looking for, because we're, for example, in this example I gave before, where I wanted to send the robot to another path, I don't necessarily want to have to, kind of babysit the robot until it gets to this other goal. Would really like it to be able to infer what the path preference is without having to give a constant assistance. So this is the question that we're trying to solve. How do we account for human path preference while preserving a low human intervention cost? And so the way we're going to approach this problem is we're going to design a sparse encoding for path preference. And just to go a little bit further on the model, we're assuming a noisy rational human model. This is kind of a common approach where we assume that the human's going to take actions to try to minimize some cost function, and the likelihood of the human taking this action is going to decrease exponentially with the increase in cost. And so this is a Markov diagram kind of representing our model here. So we can actually formulate this problem as a partially observable Markov decision process. And what we're interested in doing here is maintaining our belief over the unknown variables, so the goal and the path preference. And we're going to do this with the Bayesian update. Now, what I want to insist on here is what the complexity of this inference problem is going to be. And if we assume, for example, a discrete number of goals, if we think of a path preference as, for example, a homotopic choice, maybe right or left side of the table, there would be a discrete number of them. So the number of updates that we have to do to update the joint is equal to the number of candidate goals times the number of path preference that this could be, that there would be. Depending on how we encode the path preference, this number of this kind of cardinality of the preference space could quickly explode with the complexity of the environment. If we think of, for example, them as being homotopies, the more we add in obstacles in the environment, the more possible combinations are going to be. So we're really interested in encoding the preference such that this problem is tractable and we don't have something that kind of explodes with the size of the environment. The way we do this, I'm going to present how we end up with this encoding. We assume an environment defined where the obstacles are defined as polytopes, and they're defined by what's called their hyperplane representation. So they're defined as an intersection in between a certain number of hyperplanes. And using these hyperplanes, you can partition your space into what's called a hyperplane arrangement. And at each point in time, the robot's going to be located in one of the polytopes in the hyperplane arrangement, and it can move to another one by crossing one of these edges. So there's work from Joe Vinson and Mick Schrager's lab on how to go from a hyperplane representation to a graph where all of the nodes represent polytopes and the edges represent transitions in between polytopes that are next to each other. And as the robot moves, it's going to navigate on this graph along one of the edges. And this is how we encode path preference. We're going to say that humans' path preference is a preference over the transitions in between these nodes. So for each of these nodes, the human is going to prefer one of the neighbors that it wants the robot to transition to. So we kind of deviated from the concept of homotopies a little. But an interesting property of this is that paths that belong to different homotopy classes are also going to be encoded differently because they traverse different sequences of polytopes. And so we're going to assume the following graphical model for the problem on the right. And I'm going to spend a little bit of time on what this means. So what we're doing here is that we're breaking down our path preference vector theta into little components, and these components are pi and pj here. So for each polytope in which the robot's located in, for example, if it's at st is within polytope j. The human's preference for which outgoing neighbor is going to want to go to, let's say here it's pj. And by assuming this structure, we're making a conditional independence assumption. We're saying that conditioned on this state, the preference for the immediate neighbor and the goal of the task, the observation and all of the any of the other preferences are going to be conditionally independent. And the reason this assumption is interesting is that we no longer need to update the full joints G and theta when we're doing this Bayesian update. At each step in time, we would only need to update the prior on the current preference and on the goal of the task. So this reduces the complexity of these Bayesian updates to be the number of candidate goals times the number of outgoing edges for the current polytope. Now I'm showing this representation on the left there. We modeled the problem this way, but in practice, the components of theta, they're not going to be mutually independent. And an example of this is really simple. It's, let's say the robot currently prefers to go to neighbor psi2. Once the robot goes to this set, it's probably not going to want to go back. So once the robot arrived at the next polytope, we should sort of assume that because it wanted to take this edge, it's probably not going to want to go back. And there are ways that we can model this in this problem by tracing links in between these adjacent polytopes, which is what we do in practice in our experiments. But this is not significantly breaking the complexity of the Bayesian update, but we can trace these lines in between the neighbors if we want to have a more complex model for the human. Okay. So we ran a few experiments, and these are basically grid worlds that are of different sizes and complexities. And what we did was we posed a problem where the robot had to navigate to some goal, and there's some simulated human giving observations to the robot. We kind of hard-coded the path preference in each of these problems. So for example, in the simple map, we said that the human always preferred to go around the table counterclockwise. And what we do here is we look at the time it takes to compute optimal solutions to this and to update the belief. So we put these problems in a POMDP solver, which was probably not the optimal or efficient way to do it. But we do see that as the complexity of the problem increases, it does not take more time to update the belief. And so actually when we, this project was in collaboration with Dylan from the lab. And when we saw these results, I guess the question we were asking was, okay, it's normal that the complexity of the belief update doesn't increase, but why does it decrease even though the complexity of the world is higher? And actually we found the answer to this, and the reason was that to compute the path cost, we were using the A-star algorithm, but we kind of had a naive way to impose preference constraints. We were doing constraint checking at every iteration of A-star. And turns out that the more complex the environment is, the smaller the size of the A-star search tree. And that's why we see this reduction here. So we tried to compare different approaches in this simple world problem. And what we were interested in is how the success rate varied with the sparsity of the human intervention. So delta T here is the time in between consecutive human interventions. So if delta T is 1, the human's providing observations all the time. And as this grows to 30, corresponds to just never giving an indication because only giving an indication at the first iteration because we leave the robot 30 seconds to get to the goal. And so what we notice here is with a robot that fully complies with the human, this robot gets the best performance if the human's constantly providing information. But as the human's guidance is increasingly sparse, well, we observe this decrease in performance. What I didn't mention here is we consider that a run is a success if the robot reached the correct goal within the allotted time of 30 seconds and through the human's preferred way to get to the goal. And we created a human model that was pretty noisy. So these problems are actually very difficult to solve. What we did notice was that reasoning over path preferences led to a consistent improvement over trying to infer only the goal of the task. And the last thing we tried to do is we tried to integrate the notion of policy blending with our solution. And a policy blending formalism was introduced by one of Draken's papers. And the idea is that as the humans providing observations, we want to arbitrate in between the indications that they're giving and what the robot thinks the optimal solution to the task is. And so the way we arbitrate between humans' indications and the robots is by looking at the entropy of the distribution. By looking at the entropy of the goal and preference distribution. And by preference distribution, I mean the preference for the neighboring set. So if we're very confident in what the goal and the neighboring set are, we're going to follow the robot's policy. But as long as we're not confident, we're going to follow the human's policy. And we did observe a significant improvement in results by integrating this blending method. Okay, so as a takeaway here, we proposed a method for encoding and inferring a human's path preference online for navigation tasks with sparse human interventions. So we're still in the world of simulations, and we can see the way that in which we encoded path preference with these sets and the way that we obtained the graph are very imperfect. And there's a lot of interesting directions for future work here where we can try to integrate this with other ways to compute these sets that are maybe more relevant. And there's the area of semantic topometric mapping that's interesting. There's also other region construction algorithms that we could use to obtain larger sets. So these are very interesting directions in which we could take the problem. So yeah, as a conclusion, we first looked at the unknown environment problem. We saw that it was characterized by high amounts of model uncertainty, and we worked on this path planning solution to produce plans that are efficient, despite us not knowing what the environment's going to look like. And then we looked at the application of human-robot interaction, and we're looking for a method to incorporate human path preferences into navigation tasks.